Okay, good morning everyone. For today's session, we have with us Mr. Zaheer Abbas sir. He will be delivering his session on the topic of role of dual phase hydrophobic impregnators for inhibiting active corrosion in reinforced concrete structures. Now allow me to introduce you Zaheer Abbas sir's profile. Mr. Zaheer Abbas is a civil engineer by qualification with more than 18 years of experience spread across structural design, repair, rehabilitation, retrofitting work, and other key construction technologies. In his current national role, he heads all the product segment, including repair, protection, retrofitting, waterproofing, industrial flooring, tile fixing, sealant, and machine grout solution. As per specialist, general manager, construction system for Master Builder Solution India Private Limited. Being involved in structural design, he has been actively involved in providing complete design and build solution on repair and retrofitting of concrete structure across building, bridges, industrial and infra projects. He is currently an active member in supporting the framing up of repair guidelines as a part of technical committee for repair and retrofitting by ICI. He has earlier been the part of technical committee on the bridge repair by Maharashtra PWD. Now I request Zahir Abbas sir to start with his presentation.
Yeah. So thank you so much, and thanks a lot to the institute for giving me this opportunity. For a session on the topic which is very dear to most of the engineers who are actually involved in construction and also post-construction repair and protection of concrete structures. What we'll be doing today is the topic of the discussion, as Mr. Azaz mentioned, is about protection of corrosion. In my session, I will not be discussing, what all different types of protection, corrosion mitigation technologies, that are there available in the market. I would rather focus on one key system, one key technology, which is a dual phase corrosion inhibitor. But this is a migratory corrosion inhibitor. It is more apt and suitable for post construction, mitigation of corrosion, especially when the concrete structures are cracked, or in case there is already ensuing corrosion in the concrete structures. So this is something which is purely connected to protection and repair, a part of the concrete after the construction has been done, especially very effective for old structures which are showing active signs of corrosion. So I have already been introduced, so I'll not discuss much on that. I'll just show you in brief of what we are going to discuss today. Of course, because it is about corrosion, so we will start with what is the good intention that all civil engineers have. What is the good intention that all the owners of these structures have when the construction starts. So we'll start with that, and we'll see that however good and best intentions we do carry, there are lapses which happens and which affects the service life of the structure as originally envisaged. So and we genuinely have a problem facing the country and also globally. So we'll just touch up on that. Then we'll talk about basics of corrosion. This is just to highlight, not that perhaps we don't know this, uh, but it will connect well when we discuss later about the diagnosis and about the actual introduction of the surface applied corrosion inhibitor. So we'll talk about what are the diagnoses, basically to understand the state of corrosion in the concrete. And some of the diagnoses, when we try to study how badly the structures are corroding, some of the diagnosis is done to understand the durability aspect of the concrete as well, which gives a good interpretation of the corrosion activity in the concrete. So we'll touch upon basic methods that are covered to understand the corrosion state of the concrete, of the reinforced concrete structures. Then we'll introduce our technology, like we'll talk about the actual technology of the dual phase corrosion inhibitor, but mind the word surface applied. So it is surface applied, so it has to be a penetrative one. This is not a technology that we will talk about, putting additive into concrete while making concrete. This is rather something which we apply on the post construction applications on the concrete surface. That's why it's called surface applied penetrative corrosion inhibitor. And then we'll discuss about proof of concept. So having said what the technology is all about, we'll see that how this technology has been tested not only in labs but also on field, and what has been the conclusion and how effective it is in terms of stopping the corrosion, or perhaps inhibiting or reducing the corrosion activity in already the corroded structures, or in the structures, in the concrete structures which are cracked and corroded. So we will see its effect, and then a brief on how this is to be applied. Yeah. So this is the whole content of our presentation. Moving ahead, we'll just start with our intention. So everyone, if you look at, we all strive to have the best quality concrete. No one wants to see structures corroding, either at a later stage or at a premature state. So the intentions are clear. We all, try to enhance, have the best construction in place, and enhance the lifespan of concrete infrastructure, by the most effective construction solutions. Now that's the intention, but there is a reality to it. Uh, we have a lot of different, if you look at from the corrosion exposure point of view, the environmental condition has a big influence in terms of the corrosion activity. And that's why, even as per is code, this is an example of an en code. We have classification of, mild, severe, extreme conditions, and so forth, and so on. So what we will be talking here about is uh, about this system. So corrosion inhibitors, which are surface applied, mainly effective for providing a good inhibition of the corrosion in case of chloride induced active corrosion. Generally, we would see that whenever it comes to chloride, the concerns are much higher, because in the process of the chloride attack and the reaction that takes place, uh, the chloride ions are actually liberated as a byproduct of the reaction. You've got whatever parts per million you have got into the concrete, of chlorides, beyond a threshold, it gets liberated, or it gets sort of regenerated as part of the chemical reaction, and therefore it continues to provide, or it continues to cause the corrosion of the reinforcement steel. So what we will be talking about, not coatings, we will not discuss about surface sealers, we will also not talk about chemical resistant coatings. We are only concerned here about dual phase surface applied corrosion inhibitor, which is deeply penetrative and also effective for active chloride induced corrosion conditions. So this is what broadly we will discuss about. Uh, Now, coming to the basics of corrosion, we all know that, steel reinforcement. So all metals exist in the ore form, that is the pure metal oxide forms in which they exist. And there is a lot of energy that goes in before it is converted into sheets. It is converted into reinforcing bars, and it is a natural tendency of, like, any metal to go back to its original state. And that's why, if we do not protect the steel reinforcement, it will tend to it will tend to corrode, because it would always want to go back to its original ore state, which is the metal oxides. And in doing so, it leads to, basically, it reacts. I mean, there is a reaction that happens, with the atmospheric agents like oxygen, water, metal, and that leads to the corrosion of the reinforcement. So that's a very natural process. So that's why protection and mitigation technologies are extremely important, and that's why we primarily talk about providing covers also, so to say, to concrete, which varies depending upon the exposure conditions, right? So that's the very basic. Looking at the mechanism, we all know that corrosion is a purely electrochemical process. It needs to have an anode, it needs to have a cathode. We know that in case of the concrete construction, uh, the pH of the concrete is very high. It is 13, 14, and at that level of the pH, it has a very strong passivation layer to the steel reinforcement, and therefore it is the steel embedded in the concrete is very well protected. So there is no formation of a galvanic cell. But what happens over a period of time, for XYZ reasons? Let's say the quality of the concrete is not good, the structure is old, and there are fissures in the structure, it is unprotected over time. There is a tendency of the atmospheric agents like oxygen, water, to get and penetrate into the concrete and reach right up to the reinforcement level. And this causes an activity in the concrete, certain chemical reactions that reduces the pH of the concrete. And as a result, the passivation layer of the steel goes off. And at that instant, there is a formation of a galvanic cell. So you get an anode formed on the surface of the steel, and then a cathode forms on the surface of the steel, on the same surface of the steel. So in that situation, what happens is there is isolated cases of corrosion along the same length of the steel. So in a nutshell, we know that there has to be an anode and there has to be a cathode for the corrosion process to take place, and that's what is a natural outcome of the damage caused by the ingress of the atmospheric agents into the concrete. Once that kind of the cell is generated, corrosion of the steel starts to take place. Yeah. Now we know ferrous hydroxide, right? So it's something, in the very initial stages, when iron oxidizes at anodes, there are free electrons which are available. And in the presence of oxygen and water, there is a reaction with the hydroxyl ion, which basically leads to the formation of the hydroxide. Now, ferrous hydroxide is a very initial stage. It then combines with water and oxygen to form, FeOH3, and then FeOH3 transforms to FeO, Fe2, Fe3O4. So like this, it keeps on expanding and expanding and expanding. These are all the results. This is nothing but FeO, Fe2, Fe3O4. These are all different products of rust, and they keep on increasing in size and volume. And we know that rust can swell up to many times compared to the original volumes, and that's where it exerts a pressure on the concrete, and the reduction in the steel is a direct indication of the reduction in the load carrying capacity. So there are challenges that comes in. We know, primarily there are two types of corrosion primarily. Sulfate, though it attacks concrete, which then cracks and exposes the steel, but then purely from the passivation layer damage point of view, carbonation and chloride ions, or the chloride attack, are some of the most active corrosion damages that we see around us. And of this, in structures which are exposed to marine conditions, in structures which are exposed to soil which is having dissolved sulfates, chlorides, you see that there is a higher tendency of the corrosion activity to severely affect the reinforcement steel. Many of the structures we have seen and we have been involved in the past, and I'm sure that many of the participants here would have known or seen. Even if the structures are concrete structures are not exposed to the severely environment conditions, they are pretty much in the tropical areas, not exposed to marine conditions. um, we still see there has been cases where there is a lot of corrosion that happens in those structures much prematurely. And I think it's a well known case now. The city, like Delhi, a place called Dwarka, and like this there are many other projects that we have seen. Every exposure is not severe, but the water that is used to cure and to make concrete is highly contaminated, sometimes with sulfates, sometimes with high amount of chloride ions. And that kind of the problem after the construction is done, the building starts to show severe signs of corrosion, spalling, corrosion of the steel reinforcement. And you can understand the misery of the client, that while the building is ready to be occupied, you start to see a lot of problems in the structure, corrosion happening, spalling happening every now and then from places. One of the you would have all we would have all heard the recent news of one of the project in Delhi, where few floors got collapsed. That was a classic example, and one of the potential reason was that they have used a highly contaminated water, and they were just doing repairs, in patches, or as and when they could see the signs of corrosion happening. But perhaps unfortunately they didn't realize that it requires a much better and more robust solution that primarily attacks the active corrosion of the embedded steel, and this becomes a challenge when you already have a constructed structure. So, and then one fine day the whole floor got collapsed, so people were just having a cup of tea. And in fact there was a news, a family just came from market and they were just sitting in their drawing room, and the whole floor of the drawing room got collapsed below, and then that further collapsed below. So there were few casualties also. So this was a classic example of a pitting corrosion there, as I heard from different consultants. Um, so 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 that kind of the problems can aggravate even if the structure is in a good, not so severely exposed atmospheric conditions. uh, Carbonation, as we all know, it leads to the formation of carbonic acid, which basically, uh, you know, uh, tends to drop down the pH of the concrete. As a result, the passivation layer goes off, and then it starts the whole process. You get the, localized effect of the corrosion, which aggravates further with time. So these are some of the common cases, and you see what happens as you open the cover and you see that concrete is fissured, and you see that it is much more porous because there has been pressure of the rust, and you see that the reinforcement looks to be severely corroded. I mean, I'm sure that many of us would have seen such cases of corrosion. Coming to the chloride attack, the problem with the chloride attack, as we see, is that in the process of the chemical reaction that happens, chloride gets regenerated as a byproduct of the reaction, so it is never fully consumed. So so that's why chloride attack becomes much more active, and it becomes much more concerning if it is not properly addressed. And this basically leads to the effect of the chloride attack primarily is pitting corrosion, and you see there's a severe reduction in the cross section of the steel along the surface. It is not just at one point. Such problems can happen across multiple points on the reinforcement steel, and the potential damage it can cause is a sudden snapping of the steel reinforcement. So that's why chloride induced corrosion is considered to be much more severe, because it is a sleeping corrosion. it continues to happen because chloride is never consumed in the whole process of the reaction. If you think of carbonation attack, carbon dioxide is consumed. There has to be a consistent supply of carbon dioxide for the carbonation to take place. In case of the chloride attack, once it is crossed beyond the threshold, it is regenerated in the process, and it's continues to happen in the steel reinforcement till you see some snapping, some spalling happening on the concrete every now and then. So it is considered to be much more active and much more severe. Yeah. So this is just a representation of how the galvanic cell is formed on the surface of the steel reinforcement. So areas of the steel which are more exposed, where there is more exposure to the chloride ions, where there is more exposure to the water, or the concrete in those areas is not of good quality, that tends to become anode. And because the passivation layer tends to lose much faster in those areas compared to the next adjoining areas, that's called a halo effect. So I think this can happen at multiple location along the length of the steel reinforcement. Yeah. That's what you see. So basically what is done is this part is treated, and it becomes much more negatively charged, much more passivated, and as a result of that, this the anode now becomes cathode, and corrosion doesn't happen at cathode. But then if the because this is a localized repair, but if this part is totally not protected, or there's nothing done to protect this area, there is a tendency that this area which was earlier cathode may tend to become anode, and then there can be a reaction that happens from this to this side. So this is like a common phenomena that happens. Now, looking at inspection and condition assessment, I think these are some of the basic steps that needs to be performed to understand what happens to the concrete, how severely corroded the reinforcement is, and what is the level of corrosion activity in the reinforced concrete structure. Visual inspection, potential mapping. Now, mapping of the corrosion, basically there are various methods to understand what is the quality of the concrete and how effective it is to resist corrosion. And then for that matter, we do resistivity test. There are chemical analysis which is done, and there are a lot of other things. There is a direct measurement of the corrosion current as well that can be done. Carbonation, we all know, it's a very basic thing that is basically employed to understand what is the depth of the carbonation by basically using a phenolphthalein indicator, and it is sprayed on the surface, and then you get to understand how deeply carbonated the concrete is. But then carbonation is a very slow process. When we talk about chloride determination, generally, there is a chemical analysis. You take the powder. This is much more severe, as I said, that because chloride ions are regenerated in the process, so therefore it's a sleeping corrosion, and you get to see a very damaging impact of it if it is not addressed properly, and the protection of the structure is not properly done. So you take the material, you chemically analyze, dissolve it, and then you try to find out what is the content of the chloride ions, how contaminated it is. So the other method that is measured is electrochemical inspection method. So basically there is a direct measurement that can happen for concrete resistivity, half cell potential measurements we would have all heard, and actually corrosion rate measure. So GCOR is an instrument which directly gives the corrosion current, the rate of corrosion per centimeter square in the structure. So it's a very direct measurement of what is the corrosion activity happening. Half cell potential measurements, as we all know, is very, very popular. What it does is it basically tells what is the difference in the potential within the steel reinforcement. So basically what it tells is for corrosion to happen, there has to be a tendency of the steel or of something to release electron, and there has to be a tendency of something to accept electrons. The more is this tendency, the more is the potential between the 2 points. So that's what exactly half cell potential measurement does. If it is higher, so there are different categories of the potentials which is given by the test method, which tells that how severe is the probability of the corrosion happening. It only tells the probability of corrosion rather than the actual corrosion current. What you get here is the actual corrosion rate. Corrosion resistivity is another important, test which is conducted. This tells, the quality of the concrete. It gives a good idea about the quality of the concrete. If the resistivity is much higher, generally, then obviously, resistivity is nothing but it's a characteristic property of the material to resist the flow of current through it, or to resist the flow of charge through it. So if it has higher resistivity, definitely it is very well compacted, less porous, and the quality of the concrete is very good. So therefore, the chances of the ingress of the external agents into such a concrete will be limited or will be much lesser compared to a highly porous. This is also one measurement to understand the porosity in concrete. Yeah. So I think this gives a this if the resistivity is much higher, then the chances generally beyond 20,000 ohm, the chances of the corrosion is negligible. So there are again different classes of, like, different scale of resistivity to understand what are the chances of the corrosion activity depending upon the resistivity values. So those scale is already given and available as per the standards. Uh, so if, just so to say, you can see these are some of the scale of, depending upon the resistivity value, what can be interpreted in terms of the risk of corrosion. So that's what you see here. Will not go to the details of how it is done. This is just because all of this will be connected when I talk about dual surface penetrative corrosion inhibitor. Half cell potential measurements, I think we discussed about it. It gives the difference, it gives the potential difference between 2 points. That is, what is the, it basically tells what is the tendency of the metal to release electron. The higher is the tendency of the metal to release electron, the more is the chances that there is a lot of corrosion activity happening on the surface of the steel or in the embedded steel. So I think this gives a probability of the severity of corrosion, not the corrosion current. Similarly, this is one way. The most common way to derive to carry out the half cell potential measurements is by having this electrode, connected, and this is what is commonly followed in case, most of the time. But then, if the areas are very large, then I think you require much more faster and more accurate data collection technologies, which is what it is. So it basically uses four-wheel electrodes, like you can actually do this much, and this can actually gives you a survey of around 300 square meter per hour. At the rate of 300 square meter per hour, it can actually tell what is the, like it can give that large data in such a small time. So especially this becomes very suitable for infra projects like bridges or very very large slabs, where just at 1 or 2 points may not work. Maybe you can roll it across the entire surface, and then you can get the data of the entire area much faster and much more accurate with all results. So I think this is a very common one, which is like the earlier one is very common. This wheel one is not very commonly done. At least in India, I have not seen it. Then this is the scale which basically defines what is the probability of corrosion. Now, I'm sure that many of us would know that. So this is a common one. Then there is a linear polarization technique as well, which is basically which actually gives the corrosion current in the embedded steel reinforcement, and it's a much more direct measurement of what happens in terms of the corrosion rate. So it directly tells you what is the corrosion rate, and as per the guidelines, if you see, this is the interpretation. So if the corrosion is less than zero point 0.1 microamperes per centimeter square, condition of the rebar can be considered as passive. No corrosion is expected. So like this, it basically tells if it is more than 1 microampere per centimeter square, the condition of the rebar is highly corrosive and corrosion expected in 2 years or less. So those kind of like severe damages is expected in 2 years or less. So this is what this is what is the interpretation of the LPR test. It's one of the best tests that can be performed, and I think it is already done in India, and there are many institutes that performs this. Now, after this brief, once I will now like to introduce the technology which we wanted to discuss today, a dual phase corrosion inhibitor. Now, what do we understand by the word inhibitor? Generally, corrosion inhibitor has to resist corrosion. And the potentially damaging corrosion are of two types, carbonation as well as chlorides. Now, uh, therefore, a corrosion inhibitor has to reduce both the chloride, or it means it should be applicable both to reduce the chloride induced corrosion as well as to reduce the carbonation induced corrosion. It should be effective not only in dry conditions where the activity of corrosion is very less, but it should also be effective in high humidity environments, especially the marine conditions where we see that corrosion activity is much higher, especially and with different cycles of low, medium, and high corrosive activity because of the changes in the humidity, atmospheric conditions. Yeah. It must change the electrical properties of the steel and the concrete. That means a good corrosion inhibitor has to be reactive, and it should not adversely affect the quality of the concrete. Rather, it should only add to the quality of the concrete, not adversely affect it. So that should be the role of a corrosion inhibitor. Long service life, naturally, that's an outcome that when it basically impacts the corrosion cycle, it naturally tends to increase the service life of the structure. Corrosion inhibitors has to be not only, it is very important because it is not to be only tested in cases of the lab, but also we need to have proper testings on the field as well. So that's what we will showcase today in detail. Um so what's the difference? How does it work? So there are different type of surface applied corrosion inhibitors, but what we are talking is about a silane based dual corrosion inhibitor, deeply penetrative in nature, because it has very high quality silanes. Now if you see, silane is the smallest molecular structure in the chemical chain of the impregnators. Of all the impregnators which are possible, the lowest structure, the lowest molecular size is that of a silane. When you combine silane, what, just to give you an idea, when you combine silane you get siloxane, so which is slightly larger in size, therefore its penetration is limited. When you combine a lot of siloxane, what you get is a silicone based coating, so which has the penetration of a coating is not there, it's more of a film. So when you move towards the silicone side, it becomes a film. If you just below the silicone, when you have siloxane, it is not a deeply penetrative material, rather you can call it as a surface sealer. Yeah. But when we talk about silane, it's a true deeply penetrative material of all the impregnators that could possibly be thought of. So that's the one benefit of it. But we say it is dual. It is dual. Dual means it has some chemical attached to its molecular chain that basically responsible for passivation of the steel reinforcement. In some cases, these are amine molecules which are attached to the siloxane chain or silane chain that basically enhances the effect of the passivation layer of the steel reinforcement. Yeah, so that's why it's said that a dual phase corrosion inhibitor needs to basically strengthen the passivation layer of the steel reinforcement. Yeah, and it increases the electrical resistivity of the concrete. Now, why we use this? Why we say that it should increase the electrical resistivity of the concrete? Because if the electrical resistivity of the concrete will go up after the application of this treatment, naturally you will see that the corrosion activity will come down because it is inversely proportional. If the corrosion resistivity is higher, corrosion activity is lower. So there is a mechanism by which, as per the characteristic of the silane, or depending upon what kind of the inhibitor you are using, it does affect the resistivity of the concrete. If you're using silane, it increases the it greatly increases the resistivity, the electrical resistivity of the concrete. Why? Because silane is a hydrophobic material. So when you apply it on the concrete surface, you will see that the surface of the concrete will start to repel water. And therefore, in high humid conditions, it will be much more effective to basically, it will, treated concrete samples will still show higher resistivity compared to the untreated concrete samples. So that's a very big benefit that you get with silane based, deeply penetrative corrosion inhibitors. And then the other chemical molecule which is a part of this, that helps in the latent stage of the corrosion inhibition, you know which basically is effective in passivating the steel reinforcement. So that's the way a dual corrosion inhibitor is expected to work. In terms of its features, is a clear liquid, just like water you see. And if you look at a typical size of a coating, it is 200 nanometers. And if you see silicones, siloxane, it is much higher. And if you see the silane, it is much smaller. So therefore, the penetration of this, of the silanes is much more deeper in concrete compared to all the other impregnators which are available. It can be spray applied. It is a single component liquid. You just take it out from the bucket and spray it on the reinforced concrete structure. It will deeply penetrate, migrate, and provide resistance to the corrosion activity happening. It's a wonderful technology. As you would see that this simple liquid, how greatly it impacts the active corrosion. It is really worth looking at the results. Yeah. Concrete appearance does not change because, though it is reactive in nature, it is not a film which is just bonded to the structure of the concrete. It basically reacts and lines the pores of the concrete, and it becomes part and parcel of the concrete. Yeah. Uh, so as we say, it is a dual function. So the silane provides the benefit of water repellency because it basically makes the concrete surface hydrophobic in nature. So as a result, the concrete's water repellency goes up. The And then you have got the corrosion inhibitors. The integral corrosion inhibitor, which is part of the this molecule, which is a chemical which is added to this formulation, which basically allows the passivation of the steel reinforcement into the concrete along with the silane. So that's the dual function with which it works. uh, Now we will see some of the field applications. Now the material has been applied at almost, this technology has been applied across in for many structures. So to say, not, I would not say in India. Perhaps it will pick up in India, but this has been applied a lot in US. A lot of research has been done on this, and few extracts I'm going to share now with all of you. Yeah. Uh, we'll not talk about it. We'll straight come to the proof of the concept. So these are some of the extracts of the testing that has been performed, not only in lab but also on the field observations, both on the treated as well as on the untreated concrete samples. uh, you will see that this technology is proven to be effective in corrosion mitigation or corrosion inhibition, not only in new structures, but also it has been proven to be very good in case of old cracked structures or corroded structures. The result shows that it is more than 90% effective in terms of reducing the corrosion current in cases of active corrosion. So that's the level of corrosion effect that it provides. Now, once you apply it, there is a mechanism, there is a process. You see, all corrosion activities, all corrosion monitoring mechanisms are such that you don't see the result immediately. You have to wait for some time and observe it over a period of not less than from 6 months to 1 year, not less than, basically beyond 6 months. You have to keep monitoring it, and then you see all the deliverables starts to fall in line, the corrosion activity starts to reduce, and concrete resistivity goes up. All those effects are quite visible as you monitor it over time. Any any mechanism of corrosion is difficult to be proven, except it is a electrochemical process, like it's a induced the cathodic protection impressed current cathodic protection. In those cases we can immediately understand, but rest of the other systems which are applied on the concrete structures, you will have to wait for some time. These are non-destructive technologies, unlike others. You do it and no one even comes to know what has been applied on the structure, and you start seeing the benefit after 6 months. It starts to reduce, and it starts to basically give all those results of reducing corrosion with time, and that's where you would see it working effectively. These are some of the well-known institutes which has actually Spain, Germany, US. A lot of these institutes are actively involved in electrochemical corrosion technologies development and testing and all, and they have extensively tested surface applied corrosion inhibitors. These are some of the very complex test mechanism they did to understand the effectiveness of surface applied corrosion inhibitor, not only for effective how effective it is to resist carbonation, and how effective it is to resist the chloride attack. So I think all of that has been done. And what they did was, this was the one that basically they subjected the samples to greater than 95% humidity, put calcium chloride into it, and they made the concrete moist, and then it was applied and monitored 95 days after the start of the test. So the corroded specimens were treated with the material at around 600 square meters per hour. And as you see, the drop in the corrosion current after 100 days. So as you see, there is an activity which is going, and there are different samples, different dosages that has been applied, and you see here that there is a considerable drop happening in the corrosion activity after 100 days, or maybe after 90, 80 days. So you start to see the effect with time, how actually these kind of the technologies work. And what it measures, it gives you an idea of the increase in the resistivity. It tells the potential it starts to drop because it is effective in passivating the steel reinforcement as well. So you see that there is a drop in the electrochemical potential. There is a drop in the act if you measure. So I'll show here that there were corrosion currents also which were measured, and it was found to be quite effective. And you see the corrosion activity going, and you see here it starts to drop after application of the inhibitor. So that's the kind of the effect that it has in terms of resisting the corrosion activity. Now, if you look at this test which was done to assess the effect of chloride induced corrosion. So there was like at 50% relative humidity, 3% NaCl solution. The specimens were ponded with such a high chloride based solution, and you will see that this is a controlled sample which is uncoated. All of this is uncoated. So you will see in non corroded cracked concrete how the What you see here is MP8500CI. It's a proprietary product, but not going into that. It is being compared with amine functional silane and other technologies. So this basically is a dual phase surface applied corrosion inhibitor. It has been compared with amino functional silane, which has amine as a molecule. So these are different technologies of hydrophobic impregnators, and you will see that for non-corroded structures, both amine functional silane as well as dual phase corrosion inhibitor works almost same. I mean, the effects are same. So primarily to say that if it's a new structure, both almost both the technologies works almost same. But when it comes to pre-corroded structures, you will see that the bottom part, which is a dual phase penetrative corrosion inhibitor, gives much better result compared to the amine based, and it becomes same. The result is same even in non-corroded but cracked structures. So you've got a cases where the structures are cracked, they are subjected to the so if you have to understand how the corrosion activity is happening, so this is found to be better compared to the other type of the silates or of the other type of the surface applied corrosion inhibitors. Federal Highway Authority did a cracked beam test, using the same specimen. So they basically did the ponding and all, and then they took it out, non-cracked 0.3 mm samples treated with dual phase surface applied corrosion inhibitor, pre-corroded cracked 0.3 mm samples treated with dual phase surface applied corrosion inhibitor, and the ponding was with 3% NaCl solution. And you see here that the corrosion rate is so low compared to all other different type of the impregnators which are available in the market. So it's a very direct measurement of how this system actually works. A very simple liquid, very simple to apply, but then greatly effective in terms of in terms of uh, you know uh, reducing the active corrosion in this embedded steel reinforcement. This was a sort of a bigger scale where there were few specimens of the small slabs that were casted. They were all ponded with 5% salt solution. Now, even C solution will have 3 to 3.5% of salt NaCl. This is 5% of salt water, so severely loaded with chlorides. And 4 months total, 2 weeks wet, 2 weeks dry cycles. So you see the alternate wetting and drying of these concrete reinforced concrete specimens were done with the primary objective, because when you have alternate wetting and drying, there is a lot of ingress of the chloride that happens. So that was to create that atmosphere where the concrete specimens get more and more infused with the chloride ions, so that the condition can become much more severe. And that is when the whole thing was then assessed and measured as to how it has actually performed well. So again, we have all the reports here. If you would want, we can share those reports as well. So the corrosion current greatly dropped. Half cell potential was heavily controlled compared to the other compared to the non-treated versions of the concrete where it was uncoated. So I think we have a lot of reports on this to share, which has been done independently on such technologies, which we can share with the team. If anyone need, yeah. Then this is an impedance spectroscopy test. So another test that was performed on this, again, severely induced chloride ion penetration into the reinforced concrete structures. And it was actually the impedance measurement was taken up. I think all of this, why I'm showing a glimpse of all the tests that has been done, is to just give you an idea of how this simple liquid performs when compared with different other types of the technologies. So if you look at its effectiveness, it's very high compared to the other one. And of course, control untreated one does not have I mean, it's clearly visible. Yeah. So these are different types of the uh, penetrative corrosion inhibitors. So we can see that how deeply effective it was. On-site corrosion measurements were also taken, observations were done, and here a G-core instrument was used, and it was direct measurement of the corrosion rate after application of the dual phase surface applied corrosion inhibitor. I'm using the word dual phase SACI, which is different, as you see in case of because there are a lot of other corrosion inhibitors that exist as a technology. So this is a scale given by one institute, and the guidelines is that if it is greater than 1 microamperes per centimeter square, as I was showing earlier, it is severely affected. So it actually gives a direct measurement of the corrosion current. So it's basically an LPR test. uh, so as you see here, these are the untreated areas, so clearly the corrosion activity is very high, and you see 2 years after treatment, still you don't see the corrosion activity happening. So you can see that treated and untreated areas lying side by side, and how effective this simple liquid is to inhibit the process of corrosion is clearly observed. You can observe it very clearly here as a direct measurement of the corrosion current. This is incredible. It's not a simple outcome. It's a truly incredible outcome, because on one point we have the challenge of thinking how a simple liquid can help treat the corrosion problem to such a great extent. On the other hand, we have these results. Because generally, as a layman, when I see a simple liquid being spray applied, I would tend to feel, unless I see something being put to the steel, some wires connected to the steel, my tendency would be to think as a layman how this will work. But this does work. There is a mechanical mechanism by it works, and it's incredible to see the result. It's a direct measurement. It is direct measurement. LPR gives the direct measurement of the corrosion current. We have not only measured corrosion current, we have measured the corrosion resistivity, we have also measured the potential. So in the next slide, you will see that field trials showed that huge drop huge drop in terms of the corrosion current with time. As you see, it was applied on 26 March 2018, and as the time passes, you see the untreated samples has higher stuff, and the treated samples actually starts to reduce in corrosion. Potential difference, huge difference. Concrete resistivity goes up. So so i think i think this is a direct, this perhaps should give us an understanding that such simple, and this is a very easy to execute technology. It's a non-destructive system. Only thing is this: if we want to know how it works, and if we want to test it at any site, we have to have patience. The testing can only be done and monitored over a period of not less than 6 months, and between 6 to 1 year you can get to actually see how effectively it is bringing down the corrosion current. Yeah, it will suddenly not stop the current, but with time you will see it will starts to basically giving the good results. Resistivity will go up, corrosion current will come down, potential differences will start to reduce, because it will start working on passivation and lot of other things. So I think these are some of the ongoing. So these are the routine things, like we are doing these jobs and we're monitoring them as well. Yeah. So maybe at some point in time we will get a clear idea of how these other projects also shows the results, and which is no doubt going to be quite positive. Yeah. Now, just to give you an idea what this works on the application part, it's a very simple system, very very simple. You need to spray it. It's a mild spray, just like see this here. It needs to be very gentle spray. You don't need very high pressure. You need a very gentle spray. And you need to continue spraying until there is a rundown of the material, because that means that the concrete has stopped absorbing any further, which generally we have seen in cases of concrete that requires repairs. Generally, we have seen that rundown starts to happen at a consumption of 500 to 600 ml per square meter. So that's generally we see. So that's the approximate consumption that is to be considered for spray application. Simple equipments, you can spray it by various means. Simple knapsack, very simple to execute, mild spray equipments. You don't need very high pressure equipments because it is to be sprayed very mildly on the concrete because you want the concrete to absorb it. Yeah. So, functionality. So, I think there are different types of SACIs technologies that are available in the market. What we have discussed is about silane based, deeply penetrative technology of dual phase corrosion inhibitor. And that's what we wanted to basically conclude in terms of the effect that it imposes on the concrete. And in India, if you look at, it has a huge potential. It has truly a huge potential of usage, provided we understand that how it works. And I'm sure that this will pick up perhaps sooner than later. Right now what we are using in India is alcohol based, amino alcohol based technology. So which is very cheap, but because it is alcohol, it has the carrier is alcohol, so which basically evaporates much faster. It evaporates much faster. And the test also shows, whatever the research is that has happened, it also shows that amine alcohol based systems are not as effective as silane based dual phase systems, um, in terms of arresting the corrosion activity in case of old corroded structures or cracked structures. It is effective in case of the new structures, but um, I think that's where this simple, we have 2,300 kilometers of the coastal line, lakhs and lakhs of structures along the coastal line, jetties, jetty decks, bridges. I think this can be of great help. If it gets across to the specifications for such structures. I just give you an idea. In Japan, uh, they have all the railway structures for corrosion protection. This is the standard technology they use, for corrosion mitigation of all railway structures. It is part of a standard specification for corrosion related technologies, corrosion protection related technologies in Japanese, whatever the rail authority is called there. Yeah. So with this, I conclude my session. Thank you so much for your patience. And we are up for questions, if any. Yeah. Yeah. Azaz, over to you.
If any participant want to ask any question, they can post it in the comment box.
So if there are no questions, um, can I ask Azaz how many participants we, because I don't know where to see, how many participants are currently logged in?
Around 2025, sir.
Oh, okay, 2025. Okay, okay.
Actually, it will be uploaded on YouTube. So if any participant want to see it later on, they can see it on the YouTube channel of our department.
No problem. No.
Okay,
So
so then
so I
we can
think if there are
conclude
no
as if we
questions,
yeah, sir.
shall we conclude?
Yes, sir.
Okay, so thank you.
Thank you, sir.